Okay, so in the last class we discussed, towards the end of last class we discussed something called CSD, canonic sign digit. Basically here in every position we can have either 1, 0 or -1, and that is why it is called bit, digit, not bit, because bit beats only two possibilities, digit beats more than two possibilities. So this will give you the advantage that there is a way of encoding a decimal number so that whenever you have got a non-zero digit, like say 1 or -1, its neighbor to the left, its neighbor to the right will be 0. It can be done that way, which means roughly a W digit word will have almost 50% zeros. And these zeros help in reducing the multiplication complexity, because in a multiplication table, if you are multiplying some number by a 0 bit or 0 digit, it amounts to nothing, no change. So you can skip that upper row. So corresponding hardware also gets eliminated. That is the reason why it is done. In fact, there are powerful tools today, powerful algorithms to convert a binary number, conventional binary 2's complement number into CSD number, and just you can design even hardware for that. Just give the 16-bit binary input or 8-bit whatever input, and you get the corresponding CSD. I took some examples also. At that time, I was taking purely integers like 11, 18 and things like that. But as I told you, we will follow the convention where all the numbers are fractions between 1 to -1. So suppose FIR filter has been designed, coefficients have been designed, then you have chosen to approximate the coefficients by some numbers which are closest to that number but is in CSD form. So there is some approximation. One such example is, suppose output yn is minus 7 by 8 xn plus half xn minus 1. Okay. Now this coefficient minus 7 by 8, maybe the actual design had some other value close to minus 7 by 8, but that has been approximated to minus 7 by 8 because this is in CSD form. Minus 7 by 8, minus 1 plus 1 by 8, that is 0 into 2 to the power minus 1, 0 into 2 to the power minus 2 and 1 into 2 to the power minus 3. So minus 1 plus 2 to the power minus 3, minus 1 plus 1 by 8, and that is how you get it. Which means you see between these two powers, this is 2 to the power 0 and this is 2 to the power minus 3, I have got two zeros, this 0, this 0. So this is in a CSD form, though for fractional numbers. 1 by 2 is already a power of 2, so no question of converting into further CSD, is already in power of 2 form. So as I told you, actual coefficient that you have designed may be close to minus 7 by 8, so that is approximated to its nearest CSD number, which in this example is 7 by 8. Our task is to design a bit serial form of this FIR filter. We have already seen bit serial form of multipliers. We consider a multiplier called Neo's bit serial multiplier. Okay. And now we have to extend that philosophy not just to multiplier but to a more broader structure, that is digital filters. FIR filter first and then IIR filter. Suppose we are told what size, this is important, is 8 bit. Means xn as well as yn, they are all 8 bit bus when the bits are coming parallelly. So there are 8 bit lines and that forms a bus. But we are now considering bit serial operation, right? Bit serial. That means there will be only one line through which the bits LSB next to LSB next to LSB and dot 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 up to MSB. They will come one after another for one word. Okay, which means in terms of timing diagram, there will be only one line. You will have got one bit, next bit, okay, dot 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 dot. This is for 0th word. 0th word, that means x0, you can say I have got LSB, x0, 0. Okay. Then x 1, 0. This 0 stands for time. You can as well put it under bracket like this, bracket n, dot 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 x 7 0. This is the 0th word. Okay, but this, so 0th word cycle is broken into, is divided into 8 bit cycles. This is 1, this is 2, this is 3, like that. So in terms of index, I've got one index here, this, okay. Remember, I mean, this is the first. The way I have drawn here, it is a reversal of time axis, as though a leader, this is the leader, it comes first, followed by this, last is this. In terms of actual time, I should have like this. This is the 0th word, this is the 11th word, okay. In the 11th word, first guy that comes at this location, this is 8L plus 0, that times which comes the LSB. Okay, LSB of xn comes, then 8L plus 1, next to LSB of xn comes dot 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 8L plus 7. So at this time who comes? LSB means, I follow this notation as I have done here. Zero n, alright, 0 n, that is for the nth data, xn, nth data, so n is here, 0 means LSB, and this is the x7n MSB. So x0n, next at 8n plus 1 I have, at this point I have x1n dot 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 dot. So that is how the bits are coming through one line. At 8l plus 0, x0n, so the LSB of xn that gets in. At 8l plus 1, next bit comes in, x1n. Dot 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 at 8l plus 7, last bit, there is MSB comes, x7n. This is all for the nth word, so on and so forth, okay. But whatever we do, this job cannot be violated. This is the job. I must generate the same correct yn, maybe by the bit serial method, but should produce same correct yn, and then in a bit serial system, the output, the bits of yn also should come out through a single line, bit line, serially. First LSB of that, y0n, then y1n, then y2n, y3n, up to y7n, serially. So input will be x0n, x1n, dot 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 x7n, in that order. Output also will be y0n, y1n, y2n, dot dot dot, in that order. That will be a bit serial FIR filter. But remember, this basic equation cannot be violated. This is the actual digital filter. So whatever we do inside, bit serially, all those things, all those manipulations, but this basic equation has to be satisfied. I should generate the same yn, which the bit parallel, that is what serial system, ordinary FIR filter was generating. Fine. So let us see minus this part first. Minus 7 by 8 xn. Minus 7 by 8 xn, as I told you, this is a CSD, canonic sign digit form. So if you write like that, minus 1 into 2 to the power 0 plus 1 into 2 to the power minus 3. This is minus 7 by 8. This into xn. Okay. So suppose xn, the 8-bit word is like this, x0n, which enters the system at 8n plus 0. Okay. Earlier I made a mistake. It was, I said L and M, that L should be actually N. If I say A0n, A0n should come at 8n plus 0. Okay. A7n, I just made a mistake. Here I wrote N, here I wrote L. There is no L. A0n would come at 8n plus 0. A7n will come at 8n plus 7. A1n will come at 8n plus 1. A2n will come at 8n plus 2. Okay. There is no L. Last time I wrote L here and N here. I am sorry for that mistake. Both should be N, because it is the nth word. All the bits of nth word that are now bits serialized. And the cycles are 8n plus 0, 8n plus 1 up to 8n plus 7. In 8n plus 0, A0n goes in. At 8n plus 1, A1n goes in, so on and so forth. Okay. So this x0n, then next bit is x1n, then x2n, no comma is required, x3n, x4n, x5n, x6n, x7n. These 8 bits. They will come into the system serially. This will come first at 8n plus 0 here at this cycle. Then this will come at 8n plus 1. This will come at 8n plus 2 dot dot dot. This will come at 8n plus 7. 8n plus 7. Fine. But what I have in the equation? 2 to the power minus 3 into xn to be added with minus xn. So 2 to the power minus 3 xn bits, the bits will be shifted to the right by 3 bits and also then sign extended to the left by 3 bits because it is 2 to the power minus 3. Remember, whenever you divide a number by 2, that is 2 to the power minus 1, if you multiply it by 2 to the power minus 1, all bits get shifted to the right by 1 and the sign bit comes back. This is a sign bit, x7n, MSB. That again comes back to the sign position, MSB position, that's called sign extension. So if you do it thrice, this will occur thrice. So what will happen is, so this will go back out, this will go out, this will go x3n, this will come to this place, x3n. Okay, that will be the new word. Then it will be here, x4n. x0n goes out in the first shift only, x1n goes out in the second shift only, x2n goes out in the third shift only. Okay, and in the third shift, x3n comes to this position, LSB position. Then x4n, then at this location x5n, then here x6n, x7n. After that, this sign bit will get extended here, x7n, one extension, two extension, second extension, this is third extension. Alright, this is 2 to the power minus 3 xn. I have to add minus xn with that. Minus xn means I have to take the 2's complement, means there is minus xn, means the original word, I have to take the 2's complement. So x0n should be complemented, x1n should be complemented, alright, and 1 has to be added at the LSB. This is the job I require to do to just get this fellow, minus 7 by 8 xn. And we will do that serially. That is, I will have a system where x0n will come in at 8n plus 0, x1n will come in at 8n plus 1 and so and so. And this result also will come out bit serially. Now you see, first whom I am adding? I am adding x3n with x0 bar n. Remember, x3n comes to the system at cycle 8n plus 3. At 8n plus 0, x0n comes, at 8n plus 1, x1n comes, at 8n plus 2, x2n comes, at 8n plus 3, x3n comes. So I have to wait till that time. So at 8n plus 3, now I got this, and then x0n, which came 3 cycles ago at 8n plus 0, that I have to use now, which means that x0n I have to store in some flip-flops. How many? 3, because 1 cycle, second cycle, third cycle. For 3 cycles I have to hold. So then, and then complement. So at 8n plus 3, when this x3n comes, I have got this thing available. You add them with taking 1 as initial carry in the adder. You get a result that will come at 8n plus 3. New carry will come to this side. Again add, again result, and so on and so forth. Okay, this is what you will do for the this part. So let us see how the circuit will be. Okay, at 8n plus 0, the LSB came, then 8n plus 1, next guy came, 8n plus 2. So you can even show this here. This is the way things are coming, x0n, x1n, x2n, x3n, dot dot dot, x7n. Okay, it came at 8n plus 0, then 8n plus 1 and so on and so. But as I told you, I have to add x3n. This is the thing I have to do with x0 bar n, with a 1. x3n, as I told you last time, it comes at 8n plus 3. So that is the time my job will start, my work will start. I need x0n, then bar. So that means x0n which comes here, I have to store it, I have to make it wait through 3D. And then there is a NOT gate. I have to add, so this comes here. Let me have a switch. This switch will start at 8n plus 3. At 8n plus 3 it will touch here. So I'll get x3n, and that time I will have x0n bar coming here, and this adder, its carry, initial carry is binary 1, and that is at 8n plus 3, of course, that is the time when adding start. New result comes, new carry. Okay. Then at 8n plus 4, next guy comes x4n, and that time if you see, this comes at 8n plus 4, that time I need the next guy, x1n. So x1n came at 8n plus 1, so after 3 cycle delay, it will be available when x4n has come. Similarly, x2n which had come at 8n plus 2, after 3 cycle delay, okay, it will be available. That time I have x5n coming, because that will be cycle number 5, so on and so forth. And all will be complemented. And this will go on till what time? Till I have no extension coming up to here, x7n. x7n comes at 8n plus 7 here, and this fellow came, x4n came 4 cycles ago, so after 3 delays, 3 flip-flops, it will come at the same time, cycle number 7, and complemented you add. Okay, up till this, no problem. So 8n plus 3, 8n plus 4, 5, 6, 7. These are the 5 cycles due to which I go up to this. No sign extension required. Okay. So this will be 3 to ... 7. Then what happens? And always as you go on, previous carry will be held in flip-flop. It will come here. Sorry. Okay, 8n plus 3. Here it will be from 4, 5, ... I'll complete it later. Okay. So up to 8n plus 7, no problem. After that, what happens? 8n plus 8, the same guy is extended. At that time, x5n. Okay. This is cycle number 8. This is cycle number 7, cycle number 8. So 3 cycles ago, x5n came. After 3 delays, 3 flip-flops, 3 delays, in the cycle number 8, this will come up, complemented. At that time, this will be coming back as extended, sign extended, and I'll be adding them. Okay, then again further sign extended, same thing will continue. So next bit, so that will be cycle number 9. So 3 cycle ago, x6n came. So after 3 flip-flops, it will come in the same cycle 9, complemented, added. And again, this will come at cycle 10. Same thing will get extended further. 3 cycle ago, x7 came, x7n. Now it will be surfacing after the 3 flip-flops, added, right? So if you do that, (8n plus 8). Okay, this is how it will go. It will touch it here. And this carry thing will be like this, previous carry moves to new carry, moves to next addition. Again, once you add something, hold the carry in the flip-flop, pass it here in the next cycle. So 4, 5, it will come up to 10. So this is where this quantity will come up. Bits of this will come up. Bits of this. It will start at 8n plus 3. This is the cycle. It will start at 8n plus 3. Alright? So this will come, this fellow, this will come at 8n plus 3, then 8n plus 4 like that, through that adder output. With that now I have to add half xn minus 1. Okay, half xn minus 1. So half xn minus 1 means, for xn I wrote the bits like this, x0n, 1n, 2n like this. For xn minus 1 it will be same, x0 n minus 1, x1 n minus 1, x2 n minus 1, dot dot dot. This could be 1 or 0, this could be 1 or 0, this could be 1 or 0, but they are not same for both the numbers, x of n and x of n minus 1. Okay, and then that you are multiplying by half. So everything will be shifted to the right by 1, and there will be one sign extension. Okay, so it will be instead of x0 n minus 1, after you shift to the right by 1 because of this half multiplication, no, that will go out. x1 n minus 1 will come here. Then x2 n minus 1 will come. Dot 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 dot. x7 n minus 1, okay, and then this will be extended. You add them, you finally get the result. So this part, already this part you have to do again. Now this is coming out at 8n plus 3. With that I have to align this number. That is, I have to make sure that at 8n plus 3, this is available, so that I can happily add them with initial carry 0. Nothing is there. How to do that? What is this? x1 n minus 1. Let me go to the next page. So our purpose is this: at 8n plus 3, whatever is the output, adder output that I denoted by star, and I need to add these two to be added. So I need to do this. Alright, that is for n minus 1th word, number 1 bit. Where from I get? That is the question. Now you see, this is a very tricky thing. At what time the LSB of this come? 8n plus 3. x0n comes here at 8n plus 3. And that time I get the result here. Okay. At 8n plus 2, what was available here? It was the MSB of the previous word, n minus 1th word, isn't it? They are coming serially. x0n came at 8n plus 3, then x1n, then x2n, x2n, then at 8n plus 4, x1n, at 8n plus 5, x2n, at 8n plus 6, x3n, like that. But if I go before this, at 8n plus 2, so it will no longer be the nth word. It will be a bit of the previous word, last bit, MSB. So that time what will come here at this point? x7 n minus 1, MSB, last bit. At 8n plus 1, who will come? x6 n minus 1, dot dot dot. Alright. So I am standing at 8n plus 3. That time I have to add this with this guy. Okay. But x1 n minus 1. I am getting x7 n minus 1 at 8n plus 2. That is, if I delay it by just delayed by one cycle, then at 8n plus 3, I have got this result here. I have got x0n here. So here I will have the data which came here a cycle ago at 8n plus 2, which is x7n minus 1. So I will have x7n minus 1, I will have this output. But I am not interested in x7n minus 1, I am interested in x1n minus 1. If I increase the delay by 2, what will happen? At 8n plus 3, I have x0n. And so what will come here at 8n plus 3? That only which was here 2 cycle ago, if I make it 2 delay. 2 cycle ago will be x6n minus 1. 1 cycle ago was x7n minus 1, that is the last bit of the previous word. 2 cycle ago, last but 1 bit of the previous word, so and so. But my target is neither x7n minus 1 nor x6n minus 1. It is x1n minus 1. So I have to go on delaying. How many cycles? You will see, if I delay by 7 cycle, okay, then you will get this x1n minus 1 here. You can also verify another way. If I delayed by not 7, 8 cycle, then a very interesting thing will happen. What will come here at 8n plus 3? That thing which was here 8 cycle ago. Now currently I have got x0n and data size is 8 bit. So 8 cycle ago x0n minus 1 would come. All the 8 bits of x0n, x1n, x3, they will come later. If I delay it by this by 8d, not 7d, suppose I delay it by 8d. And this is the cycle I am standing. What is it I have here? I will have only that here which came here 8 cycle ago. Now which came here 8 cycle ago? Now at 8n plus 3, what is currently available? Currently available is x0, x0n. They are currently available. So 8 cycle ago who was available? It's a periodic over period 8, right? x0n, 1 cycle ago, x7 minus 1, 7n minus 1. Because x0n is the starting bit of nth word. If you go 1 cycle ago, I am in the previous word, n minus 1th word, and the last bit. If I go 2 cycle ago, I am in the n minus 1th word, 6th bit. Okay. That way, if I go 8 cycle ago, I will be in the n minus 1th word, 0th bit. But 0th I don't want, I want 1. So I don't need 8 delay, 7 is enough for me. That is why it is 7D. And rest will continue. Okay, rest will continue. So I have them. Alright. Now look at this previous thing. This data and this. So this will go on. Up to this there is no problem. Okay. Adder output, I will get this bit serially followed by this, followed by this, followed by this, dot, dot, dot. And I will get this after that 7 cycle delay, the flip flop I have added. I will get first this, then this, then this, then this, like this. Only problem will come when I need the extension. This file has to be extended. This was 8n plus 3, 4, 5, 6. So what is this cycle? See, 3, 4, 5, 6, 7, 8, 9, 10. So at 9, whatever I get, that has to be extended to 10. So this will continue. This is delay. Okay. So 8n plus 3, 4, 5, 6 up to 9. 8n plus 3 dot 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 up to cycle 9, it will be here. And it will be after delay 8n plus 10. Let me draw nicely. and the carry, initial carry here is 0. So I start the addition at 8n plus 3. So 8n plus 3 will be here. Result is here, and always previous carry will be fed back here. So 8n plus 4 dot to 10. So this is a bit serial realization of a FIR filter. Okay. Now we can make some engineering manipulation over this. If you forget the time taken by the inverters, the critical path will be basically this adder which is in series with another adder, so 2 adder delay. But these are all forward directions. So you can take them as edges in the forward direction. You can apply delays. If you bring in some delay here, instead of 7D it will become 8D. You need a delay here, D. The moment you delay here, everything timing will be advanced by 1 mode. 3 will become 4 because you are delaying by 1. So everything that has to be taken care of in the timing here. So 3 will become 4, 10 will become 11. This is 3 to 9, sorry. We can count again. 3, 8 plus 3, 4, 5, 6, 7, 8, 9, yeah, up to 9. So this is 9. But this timings will now change. Because I have added delay. So earlier it was 3 to 9, now it will be 8n plus 4 dot 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 9. Sorry, 4 dot 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 10. And this will be 8n plus 11. Alright, this will be 8n plus 11. Let me draw a little later away. I'm just trying to make it neater, that's all. So this is 8n plus, earlier it was 8n plus 3, now it is 8n plus 4. And 5 to 11 will be here. 8n plus 5 to 11. And you get the output. Okay. There is one more manipulation we can do. You can see the bits are coming here and they are getting delayed by 3 flip-flops, 3 delays. And the same bits are also subjected to 3 delays, D, 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 3D. So why waste the 3 delay twice? Why not use the 3 delay only once? Instead of giving the input here, give the input through this path and node 3D here. Now before, you see here, before these bits come to the delay here, then only I have a switch from cycle 3 to 7. So if I give the bits here, this switch will be from 3 to 7. Then after one cycle, it was cycle 8, 8n plus 8. So after one cycle, this will be 8n plus 8. After 2 cycle, it was 8n plus 9. So after two cycle, it will be 9. And this 10, so it will be 8n plus 10. So if you do like that, simple engineering manipulations. So bits of xn are coming here, x0n, x1n, dot 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 dot. and here it is 8n plus, as I told you, 3, 4, 5, 6, 7. This one switch to the next one. 8n plus 3, 4, 5, 10 here. This is 8n plus 3, 4, 5, 6, 7. This is 8n plus 8, 8n plus 9, 8n plus 10. This is the situation. Okay. So this x0n comes here at 8n plus 0, then x1n comes at 8n plus 1 and so and so. But I start getting output at 8n plus 4. It was 8n plus 3 when I use a Cartesian timing. It was 8n plus 4. Okay. This is a bit serial relation. This is for FIR filter. How about IIR filter? IIR filter has a loop. And as I told you, whenever there is a loop, any operation, and especially retiming and other operations, are definitely more difficult because of the feedback. Many things have to put in place. So we consider one IIR equation now. See, yn depends now on yn itself. That is why it is IIR. Yn minus 1 plus half yn minus 2 and xn. Again, we'll have 8-bit relation. Okay, we'll assume word length. Okay, and we'll go for a relation. And that time we'll discuss also that always it's not, relation may be possible, may not be possible depending on the word length and also the coefficients, other things. Okay, that we will do in the next section. Thank you very much.